All right, so remember that we started talking about object-oriented programming last week, and then we mentioned these four pillars that we'll start with today: abstraction, encapsulation, inheritance, and polymorphism. And we'll start today with abstraction and encapsulation because you're actually pretty familiar with them already with respect to other areas of computing. For example, abstraction is just a form of what's called information hiding. It's an implementation detail that is hidden away and abstracted so you don't have to worry about those details. And the classic example here is, say, the square root function, right? Or I should have asked, how does the square root function work, right? Is it a Taylor series? Is it an interpolation method? Is it a different interpolation method, right? Is it an estimate? How does it work? Does anybody know how it works? Right? Well, who cares? Who cares how it works? All right, it just does, all right? I.e., we're only interested in using it, not in how it actually works. Now, if you want to know how it actually works, it's actually quite complicated. Math.square root. Let's go ahead and take a look at that really quick. Come on, there we go. 1. All right, there we go. Come on, I can't do it right here. I'm gonna have to do it over in demo. There we go. Oops, right there. And how does it actually work? Well, it's about 100 lines of code. First of all, it hands it off to this strict math square root function, and that actually calls another function called compute, right? And then there's actually 100 lines or so here that does a bunch of bit masking and bit twiddling and other tricks and corner cases, right? You normalize X and then you do some sort of interpolation method here. It's a lot of bit level kind of stuff, right? Very, very complex, right? But at the end of the day, abstraction allows us not to have to worry about that. We just call that function, right? That's what's called procedural abstraction, right? And that's what you learn in Computer Science 1, right? That the details are hidden inside the function and we don't have to worry about them. But now think object-oriented programming. In other words, objects. How are objects abstracted, right? Well, remember that we are playing around with this local date, or local date time is another one, right? My question is, how does it represent dates, right? So if you were to have to implement this yourself, what would you do? Right? What are some options? It's like today is February 4th, 2026, right? How would you represent that? So February, there's a month. 4th, there's a day. 2026, that seems like a year to me, right? In other words, is it 3 integers? Right? Okay, is that the only way of representing dates? As we've seen already in your first project, how did we represent dates so that, or did we do that? No, I don't think that it came with dates, but we've looked at dates before, right? There's an ISO 8601 standard, right? That is something like, say, today would be 2026, and it's 02, and it is the 4th, and then what time is it right now? It is 10:33 and 49 seconds and let's just say 1,000 seconds, right? Basically what this is a lexicographically orderable string, right? It's a string, it's lexicographically orderable because it puts the year first. Then it goes with the month with leading zeros. Then it goes with the day also with the leading zeros. And then it has a T here separating the time on a 24-hour clock here. And then at the end, you can also put like CDT or I guess right now it's standard time, right? I forget what it is. But that's another way. It's an ISO 8601 standard, and it is the only proper way of representing dates in computer science because it's lexicographically orderable, right? In other words, if you compare that string to that string, then the stuff in the past comes before the stuff in the future or the present, right? It's orderable. There's another one called the Unix epoch, right? In other words, the number of seconds since January 1st, 1970, right? That's called the Unix epoch, right? And if we look it up as an example, as a Unix epoch time here. I'll go ahead and show you an example here. Yep, there's an epoch converter that we can go ahead and take a look at here. What time is it right now in your computer? It is that time right there, right? It's just one single integer number that is measured from some fixed time, January 1st, 1970. And then how do you go into the past? Well, negative values. This is the number of seconds since that time. And you can convert to any other actual time using that single number, right? So that's the Unix epoch time, which is just simply a single integer, right? But now let's go back to this local date time, or just local date if we want to keep it simple. How does it represent dates? Again, what's the answer? Who cares? It just does. All the details are hidden away from us and abstracted inside the class. If you really want to see what it looks like, I'm going to go ahead and get rid of this, get rid of this, get rid of this. And let's go back to our book example over here. Right? Remember that we were using local date, the date that I read that book. Let's go ahead and jump in there. How does it represent dates and time, an actual date here? There we go. Year, month, and day. All three of them are integers. A short integer is only 2 bytes, and that's all you need to represent a month, because a month is 1 through 12, or a day is 1 through 31. Right? So again, I would have to rip open the guts of this class in order to find that out. Abstraction allows me not to have to worry about that thing. I just have to know how to use the class, use its public-facing, public interface, basically. Right? Again, abstraction allows you to reason about an object without knowing its particular details or how it's represented. Okay? Encapsulation is kind of a complementary thing to abstraction. It's usually comprised of 3 things, what we've talked about before. The grouping of data into one logical unit, right? That's in any programming language, you're going to have something like that. In C, you have structs. In Python, you have classes as well, or tuples. And then over here in Java, we have classes to do this for us. Right? The protection of data from the outside world. In C and in Python, there is no protection of the data. Right? Everything is viewable. There is no private keyword. The grouping of methods that act on that data. We don't have that in C, but you do have that in Python classes. So Python and C, those both offer weak encapsulation. Here in Java, we have strong encapsulation. We have all 3 of these things, right? And generally, the way that we've done this up to now, right, is that all member variables should be private, like we did over here in the book class. All right, there we go. I made them all private, unless there is a very good reason to not do that and do so otherwise, right? Make sure that everything is private by default. And then you can open it up if there's a good reason. Usually I've never found a good reason, right? Remember that you can make as many constructors as you want in order to make your objects as flexible as you want, right? You're going to be doing that today in your lab. You're given, I forget what the class is, maybe it's also a book class, but you're going to be playing around with its constructors, and you'll find out that if you don't do anything, you're given this default constructor, no argument default constructor. And then you can go ahead and create a constructor, but then the default one goes away. You can also restore it explicitly. Or over here in this, we had 2 constructors. One of them that took an author because we were interested in searching for a book by author, and then one that took everything, right? All those pieces of data. We can make as many of these things as we want. And then there's also a special one called a copy constructor that I'll talk about here momentarily, right? You should also avoid setters, right? Make sure that you are preferring immutable objects. Because especially, not for this class, but eventually you're going to have to be programming for a parallel and distributed environment, right? Where you've got multiple threads acting on the same data. Now, if those threads can only read the data rather than reading and writing the data, then everything is thread safe automatically. Right? Everything that's built into Java, strings, integers, doubles, these are all immutable objects. And why? Because they prefer to be thread safety first, right? And you should as well. Let's see. So there are 2 other patterns that we might eventually get to. One of them we'll definitely get to here in a moment. Copy constructors, which I'll talk about in a moment. And then if you do the advanced activity in your lab today, I think there's what's called a builder pattern, right? So the reason that you would want to use something like that is because there's a lot of data here, right? If I went over here and created a book, right? Say let's go ahead and create a book here. Book B is equal to new book. What was the order of all those things? I think the ID was first, and then the title, I think, and then what came next, right? In other words, I'm always going to have to go back to the documentation to think what came next, what came next, what came next. Instead, what you can do is what's called a builder pattern, and it's going to be way more complicated than we're going to be able to do today, but you can do something like this. Book B is equal to book dot set title, right? And then say the title, right? Dot set ID, right? And then set the ID to 1, 2, 3, 4, and then whatever else you want on it. Basically, I am, and I don't have the code to support this because I would actually have to implement the builder pattern, so that's why it's not compiling. But you can see that it's kind of more fluent here, right? This is called a fluent pattern where you can chain these things together. Now do I have to guess anymore? Well, the first one was the ID, the second one was the title. You can go in any order that you want. And the setter here is going to tell you what you're setting, right? It's way more fluent, it's way more user-friendly. And then at the very end, you would call a function called build, right? Okay? So that's what the pattern looks like. I can actually show you one example. So we all know strings already, but we might not be familiar with string builder, right? String builder is a mutable version of the string. I can go new string builder, right? And then I can chain things together. I can append hello, right? Dot append a space, dot append world, right? World, right? There we go. And suppose I misspelled this right here. I'll go ahead and change the first one. I think you can set char at. The first character, I'll reset that to capital H there, right? All right, now that does not yet build a string, but you can see that I've chained all this. Now, it's really, really long. So what you generally do in this case is you go down to the next line here and align everything up here, right? So dot append, there we go. Dot append, and your IDE will align everything exactly for you. There we go. And now I can see it a little bit better. It's still kind of long, but that's because I've blown it up so for display purposes up here, right? You can chain these calls together, append, 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 and whatever else is in there, right? Then you can go ahead and say build. And that builds a brand new string. Let me go ahead and create a string over here instead. String S. There we go. New string builder. What's wrong with you? Build. Okay, it's not build. What is it? I think it's toString. There we go. Nope, that's not toString. What is it? Dot. All right, must have gotten it wrong here somewhere. Did I miss something? Let's go ahead and go with that. And what else? New string builder dot toString. There we go. There we go. All right, so why wasn't I able to set the character? Dot char set character. Is that not what I had? I thought that's what I had. There we go. Okay, that does not return itself for some reason. Oh, wait, nope. Try that. Nope. All right, that's not going to let me do it, but I can append, and then build it into an actual string. See that kind of pattern? That's called the builder pattern, right? And if you want to, you can explore it more in your lab 4 today in the advanced activities. Right? What I want to do is I want to look at, for the rest of the day here, I want to look at a different demonstration that really illustrates abstraction and encapsulation working together. And for that, I'm going to bring in an exercise from my CS1 book over here, right? And let's zoom in on it. Right? There we go. All right, so the rate of decay of a radioactive isotope is given in terms of its half-life h. So this is a little bit of physics or chemistry, whichever one it is. The time lapse required for the isotope to decay to 1 half-life of its original mass. For example, if I have a radioactive isotope, strontium-90, right? That has a half-life of 28.9 years, excuse me. If we start with 10 kilograms of strontium-90, then in 28 years, or 28.9 years, we would only have 5 kilograms of strontium-90. And then we would also have 5 kilograms of uridium and zirconium. Those are the isotopes that it decays into, right? So what we're going to do is we're going to write a program that takes in an atomic number, an element name, an element symbol, a half-life, right, and an initial mass, m. And then we're going to compute, the year after year of its decay. In the first year, we have, say, 10 grams, okay? That's because that's the input that I gave. Then after the first year, we only have 9.76 grams remaining, right? ... After 29 years, we only have 4.99 grams left. Because remember, the half-life was 28.9, so we have less than that, okay? So let's go ahead and write this program traditionally, right? In other words, let's not think about object-oriented programming at all. Let's go ahead and have a review here on how to do basic Java I/O programs. So first of all, I'm going to read them in as command line arguments. I need to check if the number of arguments is what I expect. If the length of the arguments is not equal to 5, then what do we do? Sorry, bad typing there. Not equal to 5. And 5, why? Because what are we reading in again? We're reading in the atomic number, element name, element symbol, half-life, and initial mass. 5 things, okay? So if the number of arguments is not 5, then we do some basic error handling here. Not too common, but we saw this on assignment 1 of people not doing proper error handling and just letting it die with a thrown exception. So I'm going to go ahead and say system.error. We didn't expect that, but we expected an error message. Println, enter 5 arguments. There we go. Now what should I do at this point? If you didn't give me enough arguments, is there enough to continue this program? Nope. So let's go ahead and exit with a non-zero error code here. Right? That way when I run this and I don't provide any command line arguments, then I'm going to get this red message that says you need to enter the proper number of command line arguments. And I had to go back and change that error message to be a little bit more verbose. Like, what do you actually need to enter as command line arguments? Otherwise, I'm going to start reading these in. And for this, I'm going to go ahead and bring it over here so that I can see off to the side here. The atomic number, what type is that? Atomic numbers are like, what's 1? 1 is helium. Hydrogen, is it? Hydrogen, there we go. Then 2 is helium. Is that right? 3, well, whatever they are, I have no idea, right? But they're integers. So int, atomic number, right, is equal to args sub 0, the first one. Now it's not compiling. Why? What do I have to do with that string that I was given as command line arguments? I have to parse them. So integer dot parse int. There we go. Now I've got my atomic number. What about the element name? Like strontium. That's going to be a string. Element name is equal to args sub 1. There's no conversion there because it's already a string to a string. What about the element symbol? Args 2, right? That's also a string. What about the half-life? Should that be an integer? Half-life of strontium 90 was what? 28.9? Is that an integer? Nope, so double. And I'll call this half-life. There you go. And to convert that, I would go double dot parse double, right? Args sub 3, okay? Almost there. Now I need a mass, right? Is that going to be an integer? Well, it could be, but are you always going to have, 10 grams or 9 grams? Can you have 9.5 grams? Yeah, definitely. So what should I do? Also a double here, right? And then double dot parse double. There we go. And arg sub 4. There. Now, how do I go about producing this table over here? Okay, let's go ahead and read this again. Right. But I definitely have my inputs already. Right? Your input, we will produce a table detailing the amount of the elements that remain after each year until 50% of the original mass remains. This amount can be computed as follows. So we take the mass, and then remember it's a half-life, so 1/2 years divided by the half-life. That's the number. That's the mass that's remaining after y years, right? Otherwise, the mass and the half-life, those were read in as command line arguments already. That's part of the input. And then years, we need to count those years, 1, 2, 3, 4, until we've reached less than half of the original mass. Okay? So what kind of a loop do you want to write here? Is it always going to be 29? Nope. So if I start, if I did a different half-life, where the half-life is several billion years, right? Then I'm going to be running for a lot longer, right? So what kind of a loop should we write? A while loop, right? And we're going to have some more stuff here, but let's go ahead and start with this. While the current mass is greater than or equal to 0.5 of the original mass, then I will continue and print things out. System.out.printf, right? And what do I want to print on each line? I want to print the year and then the amount of mass that we have. So current mass. Right? We haven't declared these things yet. This is usually a programming trick that you get used to of, okay, I want to write this out in plain English. While the current mass is greater than or equal to half of the original mass, keep going. Then I'll come back and I'll fill in the details later on. Right? So the year and the current mass, and I will need to print that out as a %d, and then tab over if you want to or whatever, and then 0.2f, because it's only 2 decimals of accuracy here. And I guess everything's in grams, so let's go ahead and put a gram and an n-line character in there. Okay? All right, before my loop now, I need that current mass, double current mass. What do I initialize it to? What do I start out with? This mass right here. Right? Right? Double and original mass. Original mass is equal to, also, I'm starting out with that mass. Now, do we actually need 3 variables here? No, you could probably get by with 2, right? But I'm doing this in a long form here because we're eventually going to redo this in an object-oriented programming fashion. Do you see any objects yet at all? No. This is what you would do in C. This is what you would probably do in Python if you'd never covered classes, right? This is what's called procedural style. I am declaring that line 1 and then line 2 comes after that, line 3 comes after that, and then we've got this procedure that does a while loop, etc. Right? Okay, let's actually print the headers too. Right? I'll show you a trick here to do that. Let's go ahead and I am not going to be able to do that. All right, fine. I won't worry about the header there. I'll just go with elapsed years, years and amount, and I'll tab over there a little bit. Right? You can come back and make it look pretty if you want to, right? But I'm just going to go ahead and do it like this, really quick. Okay, there. Now, if I were to run this, well, right now, if I were to run this, I don't have a year yet. So, what should I do with year? Int year. Where should I start that one out at? 0. Okay, let's find out if that works. Let's go ahead and now if I were to run this, I wouldn't have any command line arguments yet. So let's go ahead and run configurations, then go over to arguments and provide the arguments that you want for this. And so this was what what is strong TM? I think it's not. Is it 90? Strong TM, and it's what's the symbol? I guess it's 38. Strong TM 90 is the isotope. So 38. And then the half-life is 28.9, and SR is what it is. All right, so SR, let's go ahead and fix that one to 38. All right, and then the half-life is 28.9 years, and I'm starting out with 10 grams. Okay, so let's apply that and see if we get this to run. What happened? Am I making any progress towards my terminating condition in the while loop? No, I'm just printed out 0, 10 over and over and over again. All right, so let's stop that first. All right. All right, so what do I need to do to make progress towards this? I need to update the current mass to be the original mass times 1/2 of the year divided by the half-life. So it's just a transcription of this function right here, right? So what is it? Current mass is equal to original mass, ord mass, times 0.5 raised to the power of year over half-life. Right? Now, how do I raise it to the power there? Am I able to do that in Java? Nope. Am I able to do that in Java? You're able to do that in Python, but we can't do that here. Instead, it's math.pow, right? And we will raise 0.5 to the power of year divided by half-life. There we go. So those coming from a C background, anytime you see division here, you have to warn yourself, or you have to think to yourself, am I doing integer truncation here, right? Year and half-life. Year is definitely an integer, but half-life is a double. So do we have an issue here with integer truncation? Nope. All right, let's see if this worked. Still doesn't work here. Let's go ahead and stop it. Why? So let's come back over here. 0.5 raised to 1 divided by the half-life there. Right. Am I ever making any progress on year? Nope. So let's take care of that next. The next year is going to be year plus plus. Right? Now, if you're coming from a Python background, you're not able to do that in Python. You'd have to go plus equals 1 explicitly. But we have this nice plus plus operator here that allows us to add and increment 1 to the year each time. Right? Let's see if that does, at least gets us out of the infinite loop. Looks like it does. Except that we start out at 0, 0, and then 1. Okay. Is that what it looks like over here? No. So, one more fix over here. We're off by 1. Why is that? The first thing we do is print, right? So what should I do? I should update everything first. First of all, I will update the year, then the current mass, and then I will print out what that results in. Right? There we go. That looks a lot better, right? 1, 9.76, all the way down to 29 and 4.99. Right? Now, it doesn't look exactly like it over here because, of course, I would have to do this first line outside the loop, and I don't have this header here. But I'm satisfied, at least, with its correctness. Right? Once again, do we have any object-oriented programming here at all? No. So let's go through and make this into a more object-oriented programming style. Right? The first thing I want to do is I want to realize that there are 5 pieces of data here, right? There's an atomic number, an element name, an element symbol, half-life, and mass. Anytime that you have yourself finding more than one piece of data, 2, 3, 4, or in this case 5, and there's all one thing, an isotope, what should you be doing with this? You should be wrapping it up into a class that represents that thing so that you can do good encapsulation, the grouping of data into one logical unit. All right, I'll do that over here. Let's go ahead and collapse that so I don't have to look at it anymore. Let's go ahead and create a new class, right, just like we did with the book class, called isotope, because that's what it represents. Okay. All right, what goes into this class? I'll go ahead and get rid of book there. Well, these 5 things, right? Let me go ahead and bring that over here, right? Now, I'm not going to bring these in from command line arguments, so I'm going to have to clean this up a little bit, right? But there we go. There we go. Right, and go ahead and get rid of that. There we go, and go ahead and get rid of that. There. Okay. Step 1. I have done good encapsulation by grouping those pieces of data into one logical unit called isotope. 2, let's protect that data from the outside world. As it is right now, what I could do over here in the demo class is I could create a new isotope, strong, I'll just call it sample for now, sample, right, is equal to new isotope. Right? Now, there's no other way for me to call a constructor because remember the default constructor takes no arguments, right? But I could start setting things. Sample.atomic number is equal to atomic number. Right? And I could do that, repeat that over and over and over again. If I did that, there are two problems here. First of all, one problem is, what if I wanted to create another sample? I would repeat the 5 lines of code over and over and over again every time that I want to create this sample. Right? I don't want to do that. I want to encapsulate, that is now number 3, group the methods or behavior that act on that data inside the class. So let me come over here and let's go ahead and create a constructor. And again, you don't have to type much. You just have to go up to source, generate constructor using fields, and yes, I want to use them all. So there we go. There's my constructor now, okay? And you'll see immediately here, just like in your lab today, that default no argument constructor goes away. Right? That's fine. You can always restore it if you want to. I don't want to in this case. But atomic number, element name, element symbol, half-life, or no, that's the last thing. What is it? Half-life and mass, that is. Okay, so half-life and mass. There we go. And now you don't have to write any of those lines. That's taken care of for me over here in the isotope class. Setting all of these things is an isotope thing. Therefore, it belongs in the isotope class. Okay? So far, we've got grouping of data. We've got grouping of some methods. We'll add additional methods here momentarily. But now we want to protect that data from the outside world. As it is right now, I can see that data. I could say sample.atomic number is now equal to 90. The same mistake that I made before. And this is perfectly fine because I have not protected my variables. I've not protected my data up here. So in general, what you want to do is you want to prefer immutable objects. I want to make all of these things private. Right? Remember that trick? That's code selection mode, or the block selection mode. On a Mac, it's Option Command A. I'm sure that on Windows, it's Alt Control A or something like that. But now I've protected my data. Once I save this, you can see over here that this is not allowed anymore. Right? If you want to, you can make setters. Again, you should prefer immutable objects, but it's now protected. So we've got all three pieces of encapsulation here. The grouping of data into one logical unit, isotope class, the protection of it by making everything private, and then the grouping of some methods or behavior that act on that data. Right? Let's go ahead and save this. Let's come over here. And now let's add some other things. Right? For example, eventually I want to print out, print out information about this isotope, right? For example, maybe I would want to print out strontium 90 38 SR, right? Along with a mass or something, okay? So let's go ahead and generate a toString method to do that for us. Right? toString. And I'll let it generate with that stuff, but I'm going to come back and I'm going to change its behavior here. And I want it to look like that. Right, let me go ahead and just get rid of all that. In other words, I want it to look like the name, followed by a hyphen, followed by, or maybe that's just the name, I guess. So string.format, %s for the name, all right? And then in parentheses here, the atomic number, %d, and then the symbol, which is also a string, right? And there. Okay, we did this trick before on books, right? String.format is like, what was it called? SNPrintf or SPrintf, where you can print a formatted, a formatted version of it to a string and return that string. So this dot, what was the name? Element name. This dot atomic number. This dot symbol. There we go. All right. And now because that's included in the class, I never have to worry about that again. If I had two different samples, one strontium, one uranium or something, I would have to take that functionality out of the class and repeat it everywhere over here in the demo class. Right? As it is, though, it's already inside the class, and I don't have to worry about that. System.out.println sample. Right? Now, this is going to print before our table, so you'll see what it looks like now, and you see why I didn't even bother with it before. Right? Strontium 38 SR. Right? If I had another sample, say sample B, right? And that sample is, I don't know, what is uranium? What's the atomic number of uranium? Anybody know? Uranium. I'm pretty sure it's UR, isn't it? Its half-life is several billion years, so I'll just go ahead and mash the keyboard there, right? And we'll say that we had 1 kilogram, 10 grams. Let's go with 20 grams, actually. That's way too big. There we go. All right, that's just my estimate there. Now, I want to print out all the information with respect to sample B. Do I have to repeat myself and repeat this code over in that demo class? No. It's already where it needs to be in the isotope class, and it acts on its data instead, uranium. I guess I did 38. What is its atomic number? Somebody did it? 86, let's say, just to make it look different. I don't even know if UR is the atomic symbol, but it's different. We'll just make it up, right? Vibranium instead, if you want. Vibranium. Or no, that's what's cooler than vibranium? Adamantium, right? Right? And we'll just say that's AT. And it's super hard, so it's got to be, I don't know, 321, right? And we got 20 grams of that stuff, right? Okay? So did I have to repeat myself and repeat that code anywhere? No, it's in the class. You reuse it, right? What else might we want over here? We'll come back to that, okay? Actually, we can do other thing right now. We can go ahead and generate getters and setters, except that I am only going to do getters because I want this to be an immutable object, okay? So let's generate this now, okay? If I were thinking object-oriented programming first, I would have come and done this before I even typed out the first line of code in the demo class over here, right? I would have designed my objects first, which you're doing right now for your first phase. Design your objects and then determine how you can use those objects, and maybe that's a little bit of redesign later on, right? But ultimately, you design your objects first, your building blocks first. Instead of a top-down thing where you're taking this problem and you're breaking it up like we did initially, we are going to have our building blocks first and then build it up to the actual solution. Right? I'll go ahead and keep sample B for now. How would I change everything now that I've got that object instead? Well, my sample.getMass, right? And my sample.getMass, there we go. And then I would still have the years, right? And I would still print this out, right? Okay. So it's still going to work, right? There we go. But am I actually changing the object? Right? The current mass, where is that variable located? Well, it's located in the demo class. Does that sound right? The current mass of my isotope, that sounds like a isotope thing. Where does it belong? In the isotope class. Right? We've already got it in the isotope class, remember? It's right here, mass. So let's go ahead and get rid of the current mass. There we go. I do want to keep the original mass because that's not part of the isotope. The isotope decays, and so its mass changes. I no longer have current mass anymore. What do I have? Sample.getMass. Right, there we go. And sample.getMass. Can I set its mass like that? Can I put a function call on the left-hand side of an equals sign there? There's not a programming language that I can really think of that allows you to do something like that, right? What I want to do is I want to say, okay, well, I'm going to update its mass. Right? But remember that in good encapsulation, what I've done over here is I've said that I want to protect that data. Now, do I have a very good reason? Where is it? Where is it? Do I now have a very good reason to do otherwise? Maybe. Right? Let's go ahead and come back over here to the isotope class and now make this, instead of private, let's go ahead and make this public. Right? That'll work. Right? That issue goes away. And that's not current mass, but sample.getMass. There we go. All right, I can do that, and it'll still work, right? Okay. But basically, I've broken encapsulation here. I have bad encapsulation now because I don't have number 2. I don't have the protection of my data. Right? So let's come back over here and think of another solution. Let's go ahead and say that that's still private. And you might think, oh, well, okay, fine. Maybe there's a now very good reason here to have a setter. Let's come up here and generate setters using fields. And I don't want them all. I'll just want the mass, its setter here. There we go, and generate that. And it takes a mass and updates this object's, this sample's mass into that mass. And so over here, what I would do is I would say sample dot set mass to the original mass times all that stuff there. That's slightly better, okay? Why? Because we're setting the mass or changing the mass sounds like an isotope thing. Where does it belong? In the isotope class. Right? It's still not ideal though, right? Why is it not ideal? Because I still have some complex math here that involves decay. Decay is an isotope thing. It belongs where? In the isotope class. Just keep repeating that to yourself over and over again for the first 2 or 3 phases here, right? Because you're going to be making classes and you're going to have to decide, where does this data belong? Oh, that's a person thing. It belongs in the person class. Or that's an address thing. That belongs in the address class. Or whatever else is in the project there, right? And if you don't do that, you will have bad encapsulation. Data that's unrelated will be over here, and data, it'll be all over the place. Right? Data or behavior in this case. All right? That kind of stuff belongs in the isotope class. Right? Let me come over here, and what if I were to have a function to do this for me? Public, initially void, right? Decay. That's so much better, right? That describes the action that's happening, right? Not setting the mass. Outside the class over here, you have to determine what's the new mass, and then you put it into the class. That locates behavior outside of the class, which breaks encapsulation. We're going to take that behavior, and we're going to put it into this class right here, under a decay function, right? Now, the logic for doing that is just simply a cut and paste here and move it over here, right? Okay? So I want to decay the original mass. In this case, it's going to be this dot mass, right? So my current mass in the sample times however many years you want to decay. Well, the problem with that is I don't have years anymore. That's okay. I'll also go ahead and put it in as an integer, year, right? Go ahead and decay for a certain number of years there, right? This mass, oh, I should update this mass. This mass dot mass is equal to this dot mass, and then I decay so many years there, right? Okay. By the way, how could I have shortcutted that there? Times equals. That'll work in C or Python. I'm going to keep it like this just for now, though. Okay. Let's write our documentation for this. What is this actually doing? Right? Decays this isotope for the given number of years. There we go. Okay. For the given number of years. Right? Maybe it's better to call it years then. Years. Years. All right. Now let's do some immediate improvements before we leave today. Oh, what's wrong? Did I forget my? Oh, too many parentheses there. That should be good now. There. All right. Let's improve this just slightly, and then we'll continue to improve it on Friday. My first observation of improving things here is, what about the year? Is it always going to be a whole number? I want to decay it for a year. I want to decay it for 6 months, or a year and a half. So what should I do with that value? Make it into a double, right? That's more versatile. That is more flexible. It's more usable, right? Because you might want to decay it for 5.5 years instead of 1 year, okay? The way that we're going to use it, we're only going to do 1 year, right? But let's come over here now and actually update this code to use that, right? So sample.decay, and I'm going to do it for 1 year at a time there. I can't do it for year, by the way, because year, that increments. The first year, it'll decay 1 year. The second year, it'll decay 2 years. The third year, it'll decay 3 years. And I only want to do it for 1 year at a time. Okay? There. Let's run that, and I should get the exact same behavior. I'm not changing the behavior. I'm not changing the functionality. What I am changing here is how I interact with that object. Isn't that a lot better? How is this adhering to abstraction? The decay of a radioactive isotope is a complicated mathematical thing that I've abstracted away. You don't have to worry about it anymore. You just tell me how many years and I'll take care of it for you. Right? I'm the isotope class. How am I adhering to encapsulation? All those details are hidden away from me. and I'm interacting with it through its public interface instead of ripping out its guts and pulling out the mass and then changing the mass and then putting it back in there, right? I am keeping everything inside the class, collecting it inside the class. Right? I thought we would, let me see. We had a guest come in the last 5 minutes here. Oh, there you are. Okay, sorry, I didn't see you. So yeah, you're with the Student Advisory Board, right? And the Student Advisory Board is basically, I don't want that. Get rid of that. The Student Advisory Board is a student-led organization that interacts with faculty to improve the curriculum, feedback and stuff like that. And so she's here to talk to you about recruiting you because they are looking for officers. So I'll hand it over here.